Hello everyone. Today I will present you the history of development of the penicillin. As a summary, I will start by a definition, then I'll treat three main points, which are the prehistory of penicillin, the penicillin discovery, and the penicillin development, and I will finish my presentation by a conclusion. So, first thing first, let's start by definition. What is the penicillin? Penicillin is a group of antibiotics which include penicillin G, penicillin V, procaine penicillin, and benzathine penicillin. Those four groups of antibiotics were among the first medication to be effective against many bacterial infections caused by Staphylococcus and Streptococcus. They are still widely used today, though many types of bacteria have developed resistance following extensive use. This slide represents the timeline of evolution of penicillin from the Egyptian age into nowadays. Let's start by Egyptian age. What is the relationship between penicillin and the Egyptian age? Many ancient cultures, including those of Egypt and Greece and India, independently discovered the useful properties of fungi and plants in treating infection. This treatment often worked because many organisms, including many species of mold, that naturally produce antibiotic systems. However, ancient practitioners could not precisely identify or isolate the active component in these organisms. In 1870, the modern history of penicillin research started with this man called Burden Sanderson. The modern history of penicillin research begins in earnest in the 1870 in the UK. Sir John Scott Burden Sanderson, who observed the culture fluid covered with mold would produce no bacterial growth. Burden Sanderson's discovery promoted Joseph Lister, in his image is in the right side, an English surgeon and the father of modern antisepsis, to discover in 1871 the urine sample contaminated with the mold also did not permit the growth of the bacteria. Lister also described the antibacterial action on human tissue of species of mold he called Penicillium glaucum. Then, in 1975, John Tyndall, who followed up Burden Sanderson's work and demonstrated to the Royal Society in 1875 the antibacterial action of Penicillium fungus. By this time, Bacillus anthracis had been shown to cause anthrax, the first demonstration that a specific bacterium caused a specific disease. 2 years after, Louis Pasteur and other French biologists called Jules François Joubert observed that cultures of anthrax bacilli, when contaminated with mold, could be successfully inhibited. Some reference says that Pasteur identified the strain as Penicillium notatum. However, Paul de Cruyff in 1926 in his book Microbe Hunters described this incident as a contamination by other bacteria rather than by mold. And later, in 1895, the Italian physician Vincenzo Tiborio, who during his medical study at the Faculty of Medicine in Naples, he noticed that when the walls of a well which supplied drinking water was cleaned off, the people who drink this well's water complained of intestinal disorder. After further research, he published a paper in 1895 on the antibacterial power of some extracts of mold, making him one of several researchers who work on a mold antibiotic connection that anticipated the discovery of the drug penicillin by Alexander Fleming 35 years later. At that time, his work was disagreed and squeezed, and he received no further study. We can see at the left side the picture of Vincenzo Tiborio And at the left side, we can see the paper that he published in 19 in I'm sorry in 1895. 25 years later, in Belgium, Andre Gracia and Sarah Dath, they observed a fungal contamination in one of their Staphylococcus aureus culture that was inhibiting the growth of the bacterium. They identified the fungus as a species of penicillin and presented their observation as a paper, but it received a little attention. After 8 years, the main event in 19th century is the discovery of penicillin by Alexander Fleming in September 1928. Returning from 2 week vacation to find that a mold had developed on an accidentally contaminated Staphylococcus aureus culture plate. Upon examination of the mold, he noticed that the culture prevented the growth of Staphylococcus. So, Fleming found that his mold juice was capable of killing a wide range harmful bacteria such as Streptococcus, Meningococcus, and the diphtheria bacillus. He then set his assistant Stuart Craddock and Frederick Ridley the difficult task of isolating pure penicillin from the mold juice. Then, in 1939, at Oxford University and exactly at the Sir William Dunn School of Pathology, Howard Florey and Ernest Chain and their colleague, they turned penicillin from a laboratory curiosity into a life-saving drug. Their work on the purification and chemistry of penicillin began in earnest in 1939. To carry out a program of animal experiments and clinical trials, the team needed to process up to 500 liters of a week of mold filtrate. They began growing in a strange area of culture vessels such as bath pans, milk churns, and food tins. Later, a customized fermentation vessel was designed for ease of removing and to save space, renewing the broth beneath the surface of mold. And here we can see Flory in the front row center marked by the red circle with his group at the Oxford University and exactly at the Sir William Dunn School of Pathology. In the meanwhile, the biochemist Norman Healthy extracted penicillin from a huge volumes of filtrate coming off the production line by extraction it into amyl acetate and then back into water, using a counter current system. Also, Edward Abraham, another biochemist, who was employed to help set up production, then used the newly discovered technique of alumina column chromatography to remove impurities from the penicillin prior to clinical trials. In 1941, the first failure of penicillin treatment on February 12, a 43 years old policeman called Albert Alexander became the first recipient of the Oxford penicillin. Alexander was accidentally scratched by a raw thorn on his face, and by the end of the month, the scratch was badly infected with the both Staphylococcus and Streptococcus. He had developed a life-threatening infection with a huge abscess affection in his eyes, his face, and his legs. Penicillin was injected, and within days he made a remarkable recovery. But unfortunately, supplies of the drug ran out, and he died a few days later. Year after this failure, penicillin had known the first successful treatment. In March in March 1942, Annie Miller became the first civilian patient to be successfully treated with penicillin, lying near death at New Haven Hospital in Connecticut after miscarrying and developing an infection that led to blood poisoning. Here in the image, we can see Annie Miller in the center and in the right side we can see Alexander Fleming, and also in the left side we can see her husband, who was the director of Yale University in that time. From 1939 into 1945 was the Second World War, and the penicillin production had noted a decreasing. So, at the wartime condition made industrial production of penicillin difficult. Florey recognized that the large-scale production of penicillin was probably out of the question in Britain, where the chemical industry was fully observed in the war effort. With the support of Rockefeller Foundation, Florey and his colleague Norman Hitley traveled to the United States in the summer of 1941 to see if they could interest the American pharmaceutical industry in the effort to produce penicillin on a large scale. There where they met John Fulton, who helped to put his British colleagues in touch with individuals who might be able to assist them in their goal. They were referred to Robert Tom of the Department of Agriculture, foremost mycologist and authority of penicillin mold, and eventually the department's Northern Region Research Laboratory in Peoria, Illinois, become of because of the expertise of its fermentation division. This contact proved to be crucial in the success of project, as the NRL was a key contributor of innovation that made the large scale of production of penicillin possible. Then, with the story of increasing the yield of penicillin. So, Orville May, the director of the NRL, agreed to have the laboratory undertake a vigorous program to increase penicillin yields under the direction of Robert Coyle, who was the chief of fermentation division. It was agreed that Heatley would remain in Peoria to share his expertise with his American colleagues. Within a few weeks, Andrew Moyer found that he could significantly increase the yield of penicillin by substituting lactose for a sucrose used by the Oxford team in their culture medium. And shortly thereafter, Moyer made the even more important discovery that the addition of corn step liquor to the fermentation medium produced a tenfold increase in yield. Corn step liquor was a byproduct of the corn wet milling process, and the NLL, in an attempt to find a use for it, tried it in essentially of all its fermentation work. Later, the Peoria laboratory increased the yield of penicillin still further by the addition of penicillin precursor, such as phenylacetic acid, to the fermentation medium. And it was recognized that the Oxford group method of growing the mold on the surface of a nutrient medium was inefficient, and that growth in submerged culture would be a superior process. Florey's penicillin culture, however, produced only traces of penicillin. When growth in submerged culture under the direction of Kenneth B. Rapper, at that time, he was the staff of the NERA, screened various penicillin strains and found one of the produced acceptable yields of penicillin in submerged culture. And soon a global search was underway for better penicillin producing strains, with soil samples being sent to the NERA from around the world. And ironically, the most productive strain came from a moldy cantaloupe from a Peoria fruit market. A more productive mutant of the so-called cantaloupe strains was produced with the use of X-rays at the Carnegie Institution. When his strain was exposed to ultraviolet radiation at the University of Wisconsin, its productivity was increased still further. And in 1945, Dorothy Mary Crawford Hawkins was a British chemist who developed proteins crystallography, for which he won. I'm sorry, for which she won the Nobel Prize in Chemistry in 1964. And in 1945, she advanced the technique of X-rays crystallography, a method used to determine the three-dimensional structure of molecules. Among her most influential discoveries are the confirmation of the structure of penicillin as previously surmised by Edward Abraham and Ernst Boris Chain, and also the structure of vitamin B12, for which she became the third woman to win the Nobel Prize in Chemistry. 7 years later, Hans Magritter and Ernest Brandl in Kandel, Austria, they developed the first acid stable penicillin for oral administration V. Here we can see the two biochemists in the left side. They are working on the acid stable penicillin in their lab, and we can see at the right side the penicillin V structure. Then, in 1957, John Sheeran, the American chemist of Massachusetts Institute of Technology, he subsequently completed the first chemical synthesis of penicillin in 1957. 2 years after, the second generation semi-synthetic beta-lactam antibiotic called methicillin, designed to counter first-generation resistant penicillinases, was introduced in the United Kingdom in 1959. And penicillin in 2018. From ancient ages until nowadays, the penicillin is still used as an antibiotic against many bacterial infections. It had known many developments and huge evolutions from the mold juice and the petri dish to drugs that can be used for oral administration or as a syringe. And to conclude my presentation, I'd like to show the evolution of articles on penicillin in PubMed, and also presented with or marked with the yellow circle, we can see the decrease of the evolution of articles and also in the production of penicillin, because in that time it was the Second World time. And thank you for your attention.